A modern neural network can output a flawless, multi-threaded Python script in seconds. Yet, if you present that same model with a simple cluster of scattered dots and ask it to count them, it will fail. When given the exact prompt, "How many dots are below?" the system will reliably generate a completely incorrect, hallucinated numerical output, missing the actual dot count by a wide margin. This diagram illustrates the reality of the system's inputs. The model does not see a visual interface, nor does it process alphabetical characters. The visual data is stripped away, leaving only a stark, one-dimensional array of numerical IDs, known as tokens. Behind the text box, there is no persistent, thinking brain evaluating the request. The entity you interact with is a stateless, statistical prediction engine. It boots up, processes the sequence of numbers, emits a statistical guess for the next number in the sequence, and shuts off. These blind spots and basic logic are not software bugs that can be easily patched. They are the unavoidable, strict mechanical limits imposed by the underlying data structures the model uses to perceive the world. The system operates on the transformer architecture. The transformer is a specific type of neural network that relies on mathematical attention mechanisms to process sequential data. It functions as a rigid physical engineering pipeline, governed by extremely strict structural processing constraints. This animated sequence shows the entirety of the system's computational function. It takes a sequence of input tokens, pushes them through a fixed mathematical equation, and outputs a probability distribution. It exists entirely to produce a single statistical guess for what token comes next. Massive, energy-intensive server farms filled with high-density compute nodes are constructed for exactly this purpose. Trillions of dollars in physical infrastructure exist solely to calculate this token probability at an industrial scale. Because the hardware and architectural constraints are entirely fixed, engineers can anticipate exactly how the model will fail before a prompt is even written. Mastering interactions with a large language model requires discarding the illusion that it possesses human-like intelligence. You must understand the precise physics of the token tumbler. To compress raw internet text efficiently, models use an algorithm called byte-pair encoding. Byte-pair encoding groups the most frequent sequences of raw bytes into single, unique symbols. This process reduces the entire English language down to a vocabulary of roughly 100,000 opaque, indivisible tokens. Look at how the algorithm processes ubiquitous. The tokenizer fractures the word into 3 rigid blocks, u, bic, and itis. If asked for the third letter, it faces a mechanical impossibility. It only accesses these macro blocks, unable to see individual letters inside. This opaque block structure explains why advanced models routinely fail to count the number of R's in the word strawberry. The internal character count is entirely obscured by the boundaries of the token. Spelling failures occur because the system's architecture prioritizes the efficiency of token compression over character-level awareness. Processing these tokens involves a mechanism called a forward pass. A forward pass is the strict mathematical sequence where input data moves in one direction through the network's layers to produce an output. In this visualization, you can see that generating any single token requires an identical, fixed amount of computation. The progress bar moves at the same rate, regardless of whether the system is generating a simple conjunction or evaluating a complex logic puzzle. When a user asks the model to output the final answer to a complex math equation immediately, the system attempts to execute all of that mental arithmetic within a single forward pass. The architecture has no internal mechanism to pause and calculate. There is no variable think time. By forcing the model to cram complex logic into the fixed compute window of a single pass, the user mathematically guarantees a mathematical error. To bypass this limitation, developers prompt the model to write out its intermediate steps. By forcing the system to explain its work token by token, the incremental logic is fed back into the sequence, refreshing the context for the next forward pass. Reliable reasoning cannot happen in a single computational leap. It must be explicitly distributed across multiple output tokens to circumvent the network's fixed limit. During their initial training phase, these systems operate as base models. A base model is a raw neural network trained solely to predict the next word on a massive dataset of internet text. They act as lossy statistical compressions of the web, entirely lacking a helpful conversational persona. To transform this raw text predictor into an assistant, engineers utilize supervised fine-tuning. In this phase, human labelers write thousands of specific dialogue examples, effectively programming the artificial persona by demonstrating exactly how it should answer questions. The training data explicitly teaches the model to adopt an authoritative, definitive tone. When asked about heavily documented entities, like actor Tom Cruise, the human labelers provide clear, confident answers, which the model learns to mimic. The exact same confident posture is applied across the dataset. Whether summarizing the conquests of Genghis Khan or outlining the biography of a modern U.S. senator, the model maps its factual recall to this highly assured, definitive tone. But consider what happens when the prompt asks for a biography of Orson Kovatz, a completely fabricated, non-existent entity with zero presence in the training data. The model does not hesitate. It statistically mimics the confident tone of the human labelers it was trained on, inventing a detailed biography and citing fake accomplishments, even though its internal parameters hold absolutely no facts regarding the name. A hallucination is not a glitch in the machine's logic. It is the system successfully executing its trained conversational format, prioritizing the delivery of a confident answer over the reality of its underlying factual void. Deploying these systems effectively requires engineering around their mechanical flaws. You must establish a hard boundary between the model's internal weights and its active context window. The blurry cloud represents the network's weights, billions of adjustable parameters that encode long-term patterns into a vague, lossy recollection. By contrast, the sharp data grid represents the context window, defining exactly what the model actively holds in temporary memory with 100% fidelity. Relying on lossy internal weights to retrieve specific, niche data mathematically guarantees hallucinations. The parameters simply lack the resolution to recall rare facts perfectly. Preventing factual errors requires bypassing those internal weights entirely. You must extract the hard facts from an external source and inject them directly into the high-fidelity working memory of the context window. To automate this data injection, engineers equip the models with external tool use. The system is trained to emit special function calling tokens that pause its internal generation to interact with outside software. This interface demonstrates a model emitting a specific search start token. The moment this token is generated, the text prediction engine pauses. The surrounding software intercepts the token and executes a remote API script to query a live search engine. The raw text retrieved from that external web search is then pasted directly back into the model's high-fidelity context window, giving it perfect access to the correct information before it resumes generating its answer. This exact same mechanism allows the model to bypass its mental arithmetic bottleneck. Instead of guessing a math solution, it generates a Python script, pauses, lets an external interpreter calculate the correct answer, and reads the output back into its context window. Users and developers must stop treating large language models as omniscient, self-contained minds. They are constrained by strict physical and architectural processing limits that must be actively managed. By offloading factual recall and complex computation to external tools, you remove the reliance on lossy parameters. You transform a fragile token predictor into a highly robust, reliable reasoning system.